So we'll go ahead and get started. This first speaker today is Dalal El-Youssefi, coming from the Leibniz Institute in Leibniz Institute for Astrophysics. The talk is titled "A Comprehensive View of the Morphology of the Magellanic Clouds in the Near Infrared." And Dalal, if you want to share, I'll start the clock as soon as I hear you start talking.
All right. Hello, everyone. I'm Dalal El-Youssefi. I'm doing my PhD back at the Leibniz Institute for Astrophysics in Potsdam, Germany, under the supervision of Professor Maria Rosa Scioni. And today I'll be talking to you about the morphology of the Magellanic Clouds in the near infrared. The Magellanic Clouds are the nearest interacting pair of dwarf galaxies to the Milky Way, and so their mutual interactions, as well as proximity and resolved cell populations, deems them quite an interesting laboratory for studying galaxy morphology. And so we thought it would be quite interesting to look at the morphology of the clouds using two near-infrared surveys. The first one is the VMC survey, and it is by far the most sensitive survey of the Magellanic Clouds in the near-infrared. It has also the best spatial resolution. It observes in 3 bands, Y, J, and K, and it is multi-epoch. So it mainly covers the main bodies of both the LMC and the SMC, but also the Magellanic Bridge. But also, like the cell plate of the Magellanic Clouds, it's also quite interesting for the morphology because these regions are less gravitationally bound, and therefore they are more prone to be affected by tidal interactions. And so to look at the morphology of the Magellanic Clouds in the periphery, we used the VHS survey, which is, again, another near-infrared survey. It observes in at least 2 bands, J and K, and it covers the entire southern hemisphere when combined with the other VISTA surveys. So the aim of our study was to derive the morphology of the Magellanic Clouds using different cell populations. And in order to do so, we used a combination of color magnitude diagrams in combination with cell population models of both the LMC, the SMC, and the Milky Way. So here in the figure, we have an observed color magnitude diagram of the SMC in the J minus K versus K space. And next to it, we have the simulated color magnitude diagram in terms of age, but also in terms of metallicity. So as you see, we have various cell population boxes that we use to determine different cell populations at which we explored the morphology. So here I'm only showing a snippet of the morphological maps. So these are the highest resolution morphological maps of both the large Magellanic Cloud and the small Magellanic Cloud. So young populations showcase a rather very coherent structure where the multiple spiral arms of the galaxy are more prominent, and we also notice that the star-forming regions grow dimmer with age, while the old population, despite showing a very regular morphology and showing a rather symmetrical morphology, it still shows hints of spiral arms that are rather missing in pure old populations, such as Irregular stars, for example. When it comes to the small Magellanic Cloud, the young populations such as main sequence stars, but also red supergiants or just supergiants, depicts a broken bar, but also have protuberances in the south that are due to tidal interactions, while the old population showcases, again, regular morphology, but also elongations towards the Magellanic Bridge. And thanks to the very high resolution of these maps, we've been able to characterize irregular central features that showcase that even the inner parts of the SMC have been influenced by tidal interactions. And so now moving to the outskirts of both the LMC and the SMC using the VHS survey. As you can see, we can uncover a fair amount of substructures in the outskirts of the clouds, both in the outskirts of both the LMC and the SMC. So we confirmed the presence of substructures that were found before that we related to the interaction history of the clouds, but we also found new substructures in the eastern side of the LMC disk. So we found that these new substructures appear to be consistent with the influence of the Milky Way, reflecting the LMC disk, and the simulations show at least one structure emerging at the same location. And so mapping these futures with fainter populations and comparing their morphology to simulations will definitely provide further constraints on the orbits and the past encounters and also the mass of the galaxies. So here, thanks to both VMC and VHS, we've been able to produce high-resolution morphological maps of the Magellanic Clouds. We've used color magnitude diagrams in combination with subpopulation models to select different populations. And we traced the morphology of the clouds using H-tomography and uncovering a wealth amount of substructures. And so the upcoming step would be to try to characterize these substructures with both kinematics and chemistry, either using the available data that we have from Gaia, but also from the ESO archive. And of course, when foremost and MOOS will be available, they'll provide us with much further insight. Thank you. So yeah, if you have any questions, I'll be glad to take them.
Perfect timing. So I think everyone can see, since there's no other speakers in the room that wouldn't have access to our chat window, Christine asked a question. Do you see that, Dalal? Have you compared the stellar populations with the H1 morphologies?
The chat. Okay, so I can't, wait. So it's in the chat or in the Q&A? So in the Q&A, I can't see any questions.
Okay, so I'm sorry. It's been pointed out there's a separate tab for attendees, so I'll repeat the question. Have you compared, this is coming from Christine, have you compared the stellar populations with the measured H1 morphology, and is there any correlation between the locations of young stars and the location of the gas?
Yes, we actually did, and we did so this is a published paper, and we compared, we did a comparison of our near-infrared morphological maps with a multi-wavelength approach. So not only H1, but also like with dust maps and in other wavelengths. And we did find correlations between the spiral arms that are present in the near-infrared compared to the H1. So yes.
Thanks, Dalal.
Are there any further questions? Okay. I guess I have a question. Are there any other galaxies for which comparable work has been done in the local volume? Some of the very dwarfy or within the, I remember the paper, A Horse's Tail. It had a very nice name by Belokharov, 2008 or so. Can you do the same thing, or do you plan to do the same thing with those streams themselves?
So what we've been thinking about doing is that it'll also be interesting to look at other Magellanic irregulars in the local volume, not only just dwarf galaxies, but galaxies that are similar to both the LMC and the SMC, and that they have undergone also mutual interactions, and try to study their morphology. But unfortunately, we haven't done so far. We're still trying to get data for it, but that has been a project that we've thought of. And of course, there has been like a wealth of study looking at the dwarf galaxies in the local volume and studying their morphology.
Okay, well, it's 10:10 now, so technically we should end. For those who have, are the attendees who came in at 10 o'clock, we have a break now for 10 minutes. There was a withdrawn talk, so we're going to continue to hold that space free. So our next talk will start in 10 minutes. And it will be a 5-minute talk by Laura Cullinane. So go grab a coffee. Hi, all. Just a reminder, if you joined in the past few minutes, we're currently taking a pause to allow for a withdrawn talk so that we don't screw up the scheduled sequence of talks. So we'll be coming back live in 5 minutes. Okay, it's 10:20, 11:20, 16:20 UT. Our next speaker is Laura Cullinane at the School for Astronomy and Astrophysics at ANU, Australian National. The talk will be entitled The Magellanic Edges Survey, Exploring Origins of Stellar Substructures in the Magellanic Periphery.
Thanks, Mike. I'm Lara. I'm a PhD student at ANU, and today I'll be giving you a brief overview of my thesis work under the supervision of Dougal Mackey and Gary DaCosta on the Magellanic Edges Survey, or MAGES. The overall aim of my work is to trace the interaction history of the Magellanic Clouds. We care about this for a few reasons. One is that the Magellanic Clouds have a significant impact on the Milky Way. The Large Magellanic Cloud, or LMC in particular, substantially influences things like the orbits of stellar streams and the distribution of ultrafaint satellites, several of which it probably brought with it when it was accreted by the Milky Way. And so, in order to understand and describe these effects, we need tight constraints on the masses and orbital histories of the clouds. Another reason is that, as Dalal mentioned, the clouds are the closest pair of interacting dwarf galaxies to us. Their proximity gives us the unique opportunity to study their interactions in great detail, which we can then use to inform studies of more distant systems. So that's why we care about studying the clouds, and MAGES is the tool that we're using to do that. MAGES is a spectroscopic survey of red clump and red giant branch stars across the Magellanic Periphery. We focus on stars in the outskirts, as they're only relatively weakly bound, and therefore more susceptible to perturbation, which makes them great traces of interaction. That's evidenced when we look at maps of the Magellanic Periphery, as I've shown here on the right. This Gaia-selected map shows the number density of red clump and red giant branch stars around the clouds. Definitely what I think the most striking feature of this map is just how distorted and substructured the entire periphery of both clouds are. And all of the features we see can tell us something about the interaction history of the clouds. But in order to really understand this, what we need are 3D kinematics for stars in these features. Our Gaia gets us halfway there, providing proper motions, but the stars are too faint for Gaia to provide line-of-sight velocities. So, in order to get these, we've been doing our own survey, spectroscopically, using 2DF and AA Omega, a multi-fiber dual-beam spectrograph on the Anglo-Australian telescope. To date, we observed 26 2-degree fields, which I've shown here in red, and within each field, we observed between 50 and 350 Magellanic stars, depending on the underlying stellar density. In total, that gives us line-of-sight velocities, and therefore 3D kinematics, for several thousand individual Magellanic stars, which is the largest such sample to date, and tells us a huge amount about the interaction history of the clouds. And if you'd like to know more about the details of our survey, I'd encourage you to look up our paper, which is submitted to MNRAS and should hopefully be available soon. But what have we learned from all of this data? Let me give you a few highlights. Initially, we looked at two fields in the northern outer disk of the LMC. This field on the left is relatively far from any known substructure, while the one on the right is located near the base of this arm-like feature to the north. And as it turns out, that has a big impact on the kinematics of the two fields. The field far from the substructure has almost textbook kinematics for stars in a rotating disk, which is interesting because it's located more than 10 kiloparsec from the center of the LMC. As the rotation curve of the LMC remains flat out to this distance, which you can see in the plot on the right, that means we can use this to calculate an enclosed mass for the LMC. Our estimate is not only the most distant of recent estimates, it's also the only one to use 3D kinematics of individual stars. Others have used either proper motions or line-of-sight velocities, but not both simultaneously. Now, in contrast, if we then look at the field that's near the substructure, we find this actually has quite disturbed kinematics, including a large in-plane radial velocity dispersion that's nearly double that of the more textbook field. Additionally, in this field, a significant fraction of stars have kinematics suggesting they're moving perpendicularly out from the LMC disk, which is interesting, and what we attribute this to is the same perturbation that formed the nearby substructure. Speaking of that substructure, we find that this is actually in 3D space bending behind the plane of the LMC disk. Stars in fields along this substructure have kinematics and metallicities, which models indicate are actually formed by the basically being ripped out of the LMC disk as the LMC underwent its first infall into the Milky Way potential. And it's by combining discoveries like these with studies of the rest of the features around the clouds, which we're planning to do in the near future, that should give us a good handle on the overall interaction history and all of these interesting things that we care about of the Magellanic System.
30
So,
seconds.
I'll leave you with my summary slide. I've introduced you to majors. I've given you a couple of the science highlights with more on the way, and I'd encourage you to contact me if you have any questions. Thank you.
Okay, thank you. Very nice. Are there any questions from the audience? I don't see any. I have one question myself, which is, so you, sorry, Mike. The arm is bending away from the main body, but is it also
Yes.
bending, it's also bending away then by definition from the Milky Way itself? Is that true?
I think so. I'd have to, my 3D geometry is not great, but I believe, I mean, I think it'd be bending, I'm sorry, I'm trying to do like, figure it out in my head.
I'm just wondering if the bending away is due to some local perturbation, or is it this whole system together is affecting that bending? This might be a naive question, or it is a naive question. I know nothing about this, but it just struck me as if these two things are linked.
No worries. I mean, at least based on the models, if it's caused by the LMC like falling in, I'd assume that it's bending sort of more towards the disk of the Milky Way, is then like the LMC has come past, and so it's bending. This is sort of being pulled like backwards, but I'd have to double check that for you. I couldn't confirm 100%.
Okay. Nathan has a question with respect to the stream's arms. Is there an effect from the SMC on the bending on the top of the Milky Way infall?
If there is, it's relatively minor. I'd have to go back and double check some of the models. Yep.
Okay. We have a comment from the former AAS president. Just a comment, the stellar data set is so amazing. Gaia is transforming what we can say about galaxies. Does the presenter have comments on this? Okay.
I mean,
are we all agreed that Gaia is amazing?
Yes, I think so.
Okay. Oh, I apologize. Current, not until next week, President. Okay.
I'm
honored. All right. So seeing no further questions, we're right on track. It's 10:29 now on my clock. So our next speaker will be a longer presentation. The presenter is Rachel Frisby of Michigan State University, who will be presenting a dissertation talk, so 15-minute presentation here, on the thermal properties of the gas in early type galaxies. You can take it away if you like. We can keep on.
Had to unmute myself. All right. All right, so we're gonna switch gears a little bit away from the Milky Way and get into some fun stuff about X-rays. So I'm Rachel Frisby. I'm giving this dissertation talk on work that I've done with my PhD advisor, Megan Donahue, at Michigan State. And we're gonna talk about thermal properties of the gas in early type galaxies. We'll start with a little bit of introductory material and then highlight some results from two of the chapters of my dissertation, focusing on early type galaxies with powerful radio sources, and then also on relationships between the presence of multi-phase gas and the thermodynamic state of the circumgalactic gas in early type galaxies, and then wrap up a little bit of a summary at the end. So one of the fundamental goals of my thesis work is to understand how the energy from the central supermassive black hole in a galaxy couples to the surrounding circumgalactic gas. So understanding feedback in galaxies is fundamental to understanding how galaxies evolve, and we need multi-wavelength observations and simulations to answer this question, because it's clear, for example, from this picture of Hercules A over here, where we have the radio in blue, the X-ray in pink overlaid on the optical light. it's clear from this picture that that feedback affects the galaxy across many wavelengths. So in order to really understand it, we need to understand what's happening across all wavelengths. Early type galaxies in particular help us answer this question because they're massive and nearby, which makes them relatively easy to observe, and they can provide connections to insights learned from studies of the more massive, brightest cluster galaxies, which is a topic of the dissertation chapter I won't be talking about today. So just a little bit of contexting here. On the left-hand side, we have a picture of a galaxy with sort of the main parts of a galaxy pointed out. But what I'm actually interested in is the gas surrounding the galaxy on a much larger scale. Most of the study I've done in this dissertation has been focused on understanding how the hot X-ray emitting circumgalactic gas is evolving over time. So most of a galaxy's baryons are actually found in the circumgalactic gas. And it has, as I said before, it has a much larger radius than the optical light from a galaxy. The gas that we're concerned with emits in the soft X-ray, so about 0.6 to 2 keV. And so it's best observed by telescopes like Chandra or XMM currently. And we can see from sort of the picture of Hercules A and then through other observations and simulations that somehow the black hole is balancing feedback and cooling to maintain this X-ray gas in some sort of marginally stable state. And we can use X-ray observables to track the thermal history of the gas and find out more about what's happening in the galaxy. So how do we track the thermal history of the gas? Well, we can assume we can sort of approximate the X-ray gas as a monoatomic gas, which means we can write down the pressure in terms of entropy and density from our good old thermal physics. And we can recast that equation in terms of the X-ray observables, X-ray temperature, and the electron density, and get a quantity that we in X-ray astronomy call entropy. It's the preferred physical quantity for capturing feedback in galaxies because the density and temperature of the X-ray gas can change independently. So feedback processes don't necessarily heat the gas, but they can change the rate at which it's radiating energy, which is going to change the cooling time. So entropy captures these gains and losses of energy, and the galaxy potential well serves as essentially an entropy sorting device where the higher entropy gas rises to the outer radii and the lower entropy gas is at the small radii. And so the lowest entropy gas is the densest, brightest gas at the center of the galaxy. And the ratio of the cooling time to freefall time, where freefall time is how long it takes the gas to fall back into the black hole, tells us if the gas is cooling faster than it's falling back towards the center. So can gas precipitate out of this medium? So how do we make these measurements? If you can assume that the emissivity is constant and optically thin within a relatively thin spherical shell, which conveniently we can for X-rays, we can use a technique called deep projection, which provides us 3D source properties from two-dimensional X-ray spectra. So each annulus corresponds to a radial bin of the galaxy, and you begin by fitting a spectra with XSpec or Sherpa in the outermost annulus and work your way inwards, tying each annulus together. And so the deep projected spectral fits provide us with measurements of the X-ray temperature and the density from which we can count things like entropy and the cooling time and other useful ways of capturing the X-ray. So beginning in about 2012 with work from Norbert Werner and then continually in 2014 with more work from Werner and then Mark Voigt in 2015, they looked at the entropy profiles of a small sample of early type galaxies with Chandra data. And they found that single phase galaxies and multi-phase early type galaxies have different entropy profile slopes outside about a kiloparsec. But an interesting thing that popped out, shown in the black stars here, is the galaxy NGC 4261, which had unusually low central entropy compared to the early type galaxy observations. So rather than having a bit of a core to the entropy profile, it basically has a single power law all the way into the center of the galaxy. So we ask ourselves, why is this galaxy so much different than the other ones in the sample? And so one key difference between NGC 4261 and the rest of the sample was that it has an extremely powerful radio source, much too powerful to be just from bonding accretion alone. So we constructed an archival sample of Chandra data composed of galaxies like NGC 4261 to see if there could be other galaxies with single power law, entropy slopes, and powerful radio sources. So I extracted the deprojected entropy profiles from the soft X-rays for 12 additional galaxies. And so on the right-hand side here, you can see in the sideways triangles, those belong to the galaxy IC4296. And it turns out that IC4296 actually does have a single power law entropy profile like NGC4261. While the data resolution isn't quite as good, we can see that it follows the same single power law as NGC4261. On the left-hand side of the plot, we have data that weren't sufficiently resolved to see what was exactly happening inside the central kiloparsec. But one interesting note is that NGC315 also happens to follow approximately a power law, though the data quality is not good enough to make any conclusions about what's happening in the central kiloparsec. I also compared this data to simulations. So we compared them to simulations from Wang et al. 2018. And we see that between our data and these simulations, we actually see a pretty close similarity in the entropy profile slope. So the normalization of these profiles differs due to different parameters from the simulations. But the simulations are for a generic single phase galaxy, and they appear to match what we find for our single phase galaxies, with the added bonus of comparing to the entropy profiles from a larger sample of galaxies from Lectura et al. 2018. And those also follow this general entropy profile slope from the single phase galaxies. And another interesting bonus from exploring this is that when we take the galaxies categorized as multi-phase from the Lectura paper, they also match the multi-phase generic simulation from the Wang et al. Paper. So while there are some differences, overall the observations and simulations are beginning to agree on what multi-phase and single-phase galaxies look like. Now we're going to pivot away to relationships between the presence of multi-phase gas and the thermodynamic state of the circumgalactic gas in early type galaxies. So returning back to the 2015 paper from Voigt, they found that single phase and multi-phase galaxies have this bimodal entropy profile slope outside of about a kiloparsec, where in red we have single phase galaxies that have an entropy profile slope that goes like r to the 1. And in blue, we have multi-phase galaxies that have an entropy profile slope that goes like r to the 2/3 approximately. And an additional thing that they noticed is that the stellar velocity dispersions for single-phase galaxies were all basically higher than the stellar velocity dispersions for the multi-phase galaxies. So we think to ourselves, why might this be? We see I'll also point out this green dashed line here, which represents what the entropy profile slope would look like if supernova 1A heating was balancing the radiative cooling. And one thing that this shows out, that this indicates that'll be important in a couple slides, is that this is where the balance of radiative cooling and supernova heating is particularly relevant in the sort of 1 to 10 kiloparsec range. However, this clean bimodality that was seen in the Voigt 2015 paper became less clear in some future work done by Babak et al. In 2018 and then Lectura et al. In 2018. So they're in larger X-ray samples of about 50 or so galaxies, these correlations become less clear. However, there's a 2020 paper by Voigt currently in review where he proposes a relationship between the entropy profile slope and the velocity dispersion that arises from a theoretical model. So what this theory says is that the entropy profile slope would be dependent on the ratio between the mean specific energy of gas from stars. So this number here, epsilon star, is just the rate of stellar heat input divided by the rate of stellar mass loss. And then V sub c squared here is an alias for the stellar velocity dispersion. In this case, we're talking about the analytic model is applying to a singular isothermal sphere of stars. And so we see that the entropy profile slope is just dependent on this ratio and a couple of other factors. So we set out to explore some potential relationships between the entropy profile slope, velocity dispersion, and the presence of multi-phase gas, and then test this theoretical model from Voigt 2020 in review. So first, we took all of the galaxies with entropy profile slopes from the Lectura 2018 sample, and we fit them for a central entropy, this K naught here, for profiles that were sufficiently resolved. So here, sufficiently resolved means they need to have at least 4 points between 1 to 10 kiloparsecs, because 1 to 10 kiloparsecs is where, if the effects of the type 1a supernova could be observed, we would see that effect in the 1 to 10 kiloparsec range. And we need at least 4 points to obtain a statistically robust fit. So when we make that initial requirement for data resolution, we do find some correlation, shown here with the purple line and the confidence interval in gray.
You have 3 minutes remaining.
But when we were fitting the central entropy, it revealed that we had 2 populations of galaxies, those with a slightly boosted central entropy, so above 3 keV centimeter squared, and then those that had a slightly lower central entropy of K naught less than 3 keV centimeter squared. And the galaxies with boosted central entropy are galaxies that have likely experienced a recent feedback event that's boosted the entropy in the center, and thus they're out of equilibrium. So we wouldn't expect them to be well described by an analytic model based on something in equilibrium. So when we examine the relationship only between the galaxies without boosted central entropy, so central entropy below 3 keV centimeter squared, we find a slightly stronger correlation, again shown in the purple line with the gray confidence interval. Finally, for galaxies that have velocity dispersion below 200 kilometers per second, they might not have well-developed circumgalactic gas, and furthermore, there's no reason to believe that the Voigt 2020 model would be able to describe these galaxies with very low velocity dispersion. For galaxies that have velocity dispersion greater than 300 kilometers per second or so, numerical integration of the model reveals that the analytic model actually overpredicts the relationship above an entropy profile slope of about 1.2. And this is likely because this analytic prediction assumes a singular isothermal sphere, which is simplifying the stellar mass profile, where the numerical integration uses a more accurate stellar mass profile. Some of the other galaxies, most notably this point down here, which is for M87, are galaxies that are present in groups of galaxies, meaning that their velocity dispersions are going to be more reflective of the potential well of the group rather than the isolated galaxy. So when we make this, when we isolate this range of velocity dispersion, we find the correlation in the black dashed line here. So the correlation is once again a little bit stronger, but the most interesting thing here is the burgundy dashed dotted line is the analytic prediction, and we find that it actually matches the data very well over the area at which we would expect sort of our best chance for a relationship between the entropy profile slope and the velocity dispersion.
1 minute.
And so with that, I'll just highlight the conclusions main conclusions from the first paper. So there are galaxies with single power law entropy profile slopes like NGC 4261, though it may be a rare possibility. If the ratio of the cooling time to the freefall time is lowest in the central bin, it may indicate the presence of a powerful radio source. I didn't cover that in this talk, but you can check out the paper when it is posted. And then data and simulations of entropy profiles show similarities. And then for the second paper I talked about, we do see a relationship between entropy profile slope, velocity dispersion, and gas extent when we use a more uniform selection criteria. And for the best case sample, we actually find very good agreement with theoretical predictions. And so with that, I'd just like to thank my PhD advisor, Megan Donahue, and my collaborators. And I'll take any questions.
Excellent. There are no questions yet. So I'll start off with the question as you're entering into the job market. What will future X-ray telescopes tell us about this question? For example, does LINX give us any particular benefit?
LINX will be spectacular for this sort of thing. So one of the main things holding back understanding what's happening in the central kiloparsec is data resolution. And so having an X-ray telescope that can finally sample what's going on in the very center of these galaxies will provide very important clues as to what's happening with AGN feedback in the center of the galaxies. So that's a very exciting prospect for this particular sort of study.
Okay. I have another question. When you say feedback, are you referring to only AGN feedback, or some of these galaxies, some of these early type galaxies may have recent star formation? Is that an issue, or is that a contribution in feedback, or is it generally just the feedback from the AGN itself that's
So
disturbing?
one of the ideas we're trying to illustrate in this second paper, where we're sort of diving into the correlation in velocity dispersion and entropy profile slope, is that over these smaller radii, the type 1a supernova do have a measurable and important effect on the entropy profile slope. So the AGN feedback is important, but also the stars are important, which is something that's sometimes underappreciated in the X-ray community. And so it's been an interesting exploration to find out just how much we can learn about feedback when we're considering everything in the galaxy.
We have a question from the audience. If single versus multi-phase gas is a distinguishing characteristic, does it matter how the gas is divided between the different phases?
So amount-wise, I'm not sure. That's something I'd have to look into. But one thing that is sort of a subtlety in multi-phase versus single-phase galaxies is that all galaxies have a little bit of multi-phase gas sort of right around the center. Like basically, almost all of them have a small amount that's sort of right around the black hole. But when we're talking about multi-phase gas extent, what matters is that we have extended multi-phase gas, so something outside just the very center of the galaxy. So, for instance, the Lactura classification is a galaxy is considered multi-phase if it has multi-phase gas outside of 2 kiloparsecs. And then there's sort of an intermediate classification where you have multi-phase gas inside of 2 kiloparsecs. And then the single-phase galaxies are ones that have little to no multi-phase gas. So you might, with most data resolution, you might not actually be able to see it. So I hope that sort of answers the question a little bit. We could talk about it more offline if I can check on that for you.
Just to clarify, multi-phase, so you have the X-ray, the very hot 10 million degree, but you're referring to multi-phase as being the contribution from the cooler, the coronal 500,000 or so?
Yeah, things like H alpha mostly is what we do observations of. Yeah. Okay.
Well, I maybe this was the way the question was going. I don't want to assume, but you know, from COS, there's observations of oxygen 6 out to 150 kiloparsecs in these galaxies, and some of that gas might be in this this inflowing material. Some of it may be outflow as well from feedback processes in the galaxies, and so that's just a comment.
Yeah, I am also interested in UV in brightest cluster galaxies, but I haven't looked at UV in these types of galaxies.
Okay. We have 2 minutes to the next speaker. Do we want to, I realize I haven't been thanking people because you can't applause, so I just want to thank everyone verbally now. But this was a very nice talk. So we'll go ahead and transition to the next speaker now. Thank you. The next speaker is Christine Svekin from the Royal Military College of Canada, speaking on predicting the resolved WALLABY velocity function.
Sorry, I'll unmute. Can you see the presentation?
Yes, yes.
Okay, and I'm going to keep my video off just to make sure that the connection is fast enough, if that's okay. So what I want to do today is tell you about some work that we've done to predict the spatially resolved H1 velocity function of local galaxies that a new survey called WALLABY on a new telescope called ASCAP will deliver in the next couple of years. And a picture of ASCAP is what's shown on this slide. So to start, the velocity function is a property of the local galaxy population. It's the number density of galaxies of a given rotation velocity as a function of that rotation velocity. So you can sort of think of it as an analog to the luminosity function. Now, because we're talking about rotation velocity, I'm going to restrict what I'll discuss today to local disk galaxies. And I'm going to also restrict my the talk to the H1 rich galaxies or gas rich galaxies. So I'm going to talk about the H1 velocity function specifically. And there have been measures of the H1 velocity function that have been carried out before. And so this slide summarizes the current state of affairs. The two colored lines show measures of the H1 velocity function for the local galaxy population. And the black lines show different predictions for that velocity function. The solid line is a prediction from a dark matter only simulation. And the dashed line, the dashed black line, is a prediction from a hydrodynamical simulation. And clearly below about 70 kilometers per second, the black lines and the colored lines don't match up very well. And so there's been a lot of work invested into trying to understand where that difference arises. And one thing to keep in mind is that we're not necessarily comparing apples to apples here, in the sense that the data often come from a measure of the width of the H1 spectral line from a spatially unresolved observation at a facility like Arecibo. And so the width of the line combined with the inclination of the corresponding source gives us the point that is ultimately put into the velocity function. Whereas the simulations are often predicting V halo, which is the peak velocity implied by the mass distribution of the dark matter halo. And so there's been a lot of work trying to reconcile VH1 and V halo for local volume galaxies, invoking everything from measurement errors to baryonic effects, dark matter physics. But the point here is that progress is difficult because there's no spatial information in the observations. So if we don't know how those galaxies are, what they look like morphologically or kinematically, it's very difficult to relate the two. And so this is where the WALLABY survey on ASCAP comes in. So this again is a picture of the ASCAP telescope in Western Australia. And WALLABY will be one of the higher priority surveys that ASCAP will undertake. So WALLABY is a Southern Sky H1 survey at 30 arcsecond resolution. It's going to start in 2021. So we're taking pilot survey data now. And so for the H1 experts, it will have the same sensitivity as the alfalfa single dish survey, but 10 times the spatial resolution. And what that means is that instead of just detecting objects, we're going to spatially resolve a lot of them. And so instead of H1 spectra, we'll actually get H1 maps. And the number of H1 maps that we expect to get, or how well resolved those galaxies will be, is shown by the histogram on the left-hand side. But we predict that WALLABY will spatially resolve more than 10,000 H1 disks. And so you can actually start to do statistics of H1 morphology and kinematics in the local universe, which is something we haven't been able to do so far. So in order to extract the science from these detections, we have to be able to model their morphology and kinematics. And there are lots of different ways to go about that. And I'm the chair of the working group that's looking into how to do this in an automated way for WALLABY.
1 minute.
But so my PhD student, Colin Lewis, asked the following question, coming back to the velocity function. How well can the alfalfa velocity function be recovered from spatially resolved galaxies detected by a WALLABY-like survey? In other words, how well can we do in constructing a spatially resolved velocity function from WALLABY data? And so what he did is he generated a suite of mock H1 data cubes starting from an H1 mass to produce a realistic, a physically reasonable model of a galaxy embedded in WALLABY-like cubes. And what you're looking at here are adjacent channel maps from that cube. And this is a code that will be publicly released through the Serata project up in Canada. And he then used those mock H1 cubes to benchmark modeling codes so that he could simulate a WALLABY volume and construct a spatially resolved velocity function. And here's what he found. The black line shows the input velocity function into the survey volume. And the green shaded area shows how well he can recover that velocity function. And we find that we can recover the velocity function down to about 30 kilometers per second. And that's interesting because at 30 kilometers per second, we're into the regime where there was a discrepancy between the simulations and the observations in the single dish data. So WALLABY will actually be able to address this by resolving individual galaxies instead of trying to correct VH1 and V halo without any spatial information. And I will put up my conclusions and stop there. Thanks.
Okay, thank you very much. We are right on time. Any questions from the audience? We have a question. What does n beams greater than 3.5 mean?
Sure. So radio astronomers call resolution elements beams. And what we found from our benchmarking is that as long as there were more than 3.5 resolution elements across the major axis of the H1 disk, then we could model it reliably enough to extract a rotation velocity. And so how well we can model the disks goes into how well we can recover the velocity function, because when you're going for a spatially resolved velocity function, you have to not only detect the galaxy, but you have to spatially resolve it well enough to estimate a rotation velocity.
Okay. Any further questions? The question is, how far away will WALLABY be able to make these measurements for the low rotational velocity galaxies?
Obviously the lower mass galaxies have lower H1 masses, and because WALLABY is a blind survey, it means it's going to be able to see more distant, more massive galaxies farther away than nearby galaxies. So a galaxy like that has an H1 mass of 10 to the 10 solar masses, so that's a couple of times bigger than the Milky Way's H1 mass, that will resolve out to about 100 megaparsecs. Galaxies more like, say, the LMC that are down at 10 to the 9 in H1 mass, a little bit lower than 10 to the 9, that'll be out to a few tens of megaparsecs. The very lowest mass things that we can reliably recover, again, in terms of H1 mass, is probably about 10 to the 6 or 10 to the 7, and that will only be out to a couple of megaparsecs. For people who are familiar with the local volume, if you take an object like Leo P or Leo T, which are some of the lowest mass disk galaxies that we know of, those will be able to see out to about 4 megaparsecs, although we won't resolve them out that far.
Okay. We still have 2 minutes, so if there's any questions remaining. So the response is, so we're going to get a good sampling of the local group. We'll be able, is that true statement?
Yes, so not only will we get a good response of the local group, but we'll get just beyond the local group. And for those galaxies, I'm going to elaborate a bit because we have a minute. But when you're looking for really low mass galaxies that are bound to the Milky Way, it's really hard to distinguish between them and high velocity clouds. In other words, if you see an H1 source in the sky and you think it's nearby, it's unclear whether it's a small galaxy or a high velocity cloud. And because they overlap in velocity. And so if you can get out to a couple of megaparsecs, you avoid that problem because you're in a velocity regime where the two don't overlap, a spectral regime. And so WALLABY, even if it can only go out to a couple of megaparsecs, will go a long way towards understanding gas-rich satellite populations around nearby galaxies. And again, it's going to cover 3/4 of the sky. And so there's going to be lots of statistics in there at those mass levels.
I had seen Deidre Hunter on the attendance list. I don't see her on anymore, but so in comparison to alfalfa, in alfalfa, there's this limitation of H1 clouds, but WALLABY will supersede that. Is that true?
So WALLABY will be able to get, because it covers more sky, a lot more sky. So alfalfa covered about 7,000 square degrees, and WALLABY will cover 32,000 square degrees. So it will be possible to sample nearby galaxies much more thoroughly with WALLABY than with alfalfa due to sky coverage. So we'll be able to look at nearby galaxies where there's no confusion with the Milky Way's high velocity cloud population in order to investigate the properties of the low mass gas rich galaxies around that object. And in the Milky Way, as well as in M31, there's some confusion between high velocity clouds and low mass galaxies. So WALLABY should be able to get around that to some extent.
Okay. I'm sorry, I think I was thinking little things, not alfalfa, but same. Okay, the last speaker, it's noon now, East Coast. So Nathan, our final speaker for the session is Nathan Degg from Queen's University in Canada. The talk is titled Asymmetries as a Tool for Quantifying Velocity Profiles. Floor is yours.
Sweet. Just 1 second here. Seem to still be muted. Can you hear me?
Loud and clear.
Okay, good. Okay, well, thank you very much for having me. I'm very excited to talk to you today about quantifying velocity profiles using asymmetries, which is work I've done with Sarah Blythe, Nadine Hanks, Simon Kruger, and Claude Carignan. Now, it's really lucky that we were talking about velocity profiles just now, because we usually picture this is what I'm focused on. And we usually picture these beautiful double-horned profiles, but the reality is they often look more like CIG 421, where they're disturbed and they're not symmetric. And there's a variety of reasons why they can be disturbed. Mergers are a chief suspect, but tidal encounters, star formation, ramp pressure stripping, etc. And so what we want to do is look at a velocity profile, quantify that asymmetry, and eventually be able to get back to use those to understand the physical processes. Now, people have been working on this for a while, and they usually use the lopsidedness statistic, where you look at the flux on either side of the systemic velocity. In our work, we introduced two new methods, a channel-by-channel asymmetry, where you choose some folding velocity, not necessarily the systemic velocity, and you compare the pairs of channels on either side. The other statistic that we introduced is the velocity of equality, where you find the velocity where the flux is equal on either side, and you compare it to the systemic velocity and you normalize it by the width. Now, we did a lot of work with this, but I'm going to focus on work that we did using 115 profiles from the WISP sample of spiral and irregular galaxies, and these are H1 profiles. And on the right, you can see the lopsidedness and velocity of equality correlations. And in each panel, we're looking at points that are colored according to something that we've also quantified by particularly the visually classified asymmetry, central dip, peak width, and other quantities. And I want to highlight here the number of peaks in the central dip. And the number of peaks, blue points have two peaks, red points have a single peak, and in this parameter space, they're very well separated. It turns out this separation is actually due to the central dip, where green points have no dip, blue points have a dip above 50% of the peak flux, and red points are below 50%. And the point here is that these asymmetry statistics are actually sensitive to something physically meaningful about the profile and possibly about the galaxy itself. We also looked at the channel by channel, and again, you have this very confusing plot where you've got all sorts of things going on, and I'm going to highlight the visual asymmetry. Now here, red points we classified as symmetric, blue were slightly asymmetric, green were moderately asymmetric, and magenta are very asymmetric. And if you sweep your eyes left to right along the lopsidedness, it's very mixed together, but if you sweep your eyes from top to bottom, you get to see a little bit more separation between the points. And that's made a bit more clear in these histograms, where in the top left you see the lopsidedness, and it's very mixed together. In the bottom right, you see our channel by channel asymmetry, where again, they're still mixing, but there's better separation. So the point here is that our newly introduced channel by channel asymmetry, it does the best job of matching a visually determined asymmetry. So I'm going to finish here just saying that these velocity profile asymmetries are sensitive to important physical processes. We've introduced two new methods, and you can use these methods when you look at the entire parameter space, particularly when we think of large upcoming surveys, to infer galaxy properties and look at differences in environmental effects and between populations, and that their channel by channel asymmetry has the best correlations with visually determined asymmetries. And I will finish here and thank you for your time and welcome any questions that you have.
Okay, you were early. I've never had an early ending. We have a question from the audience. Is visually classified asymmetry done by people or an algorithm? If an algorithm, what is it looking at?
So this was done by people. It was three of us, the authors, myself, Sarah, Nadine. We classified all the profiles individually, and then we looked at how we classified them, and we had a lot of differences. And so we went through the ones that were different and talked our way through what classification. There were a lot that were in our sort of 0.5 of it's above symmetric, but it's not quite slightly asymmetric and that sort of thing. So it's a messy process, but it was done by people.
Okay, thank you. I have a question, and the number of peaks. There's no resolution issue here. These galaxies are all at comparable distances. The spatial resolution or the spectral resolution is this. We can assume it's the same.
Yeah, well, the spectral resolution, WISP does a funny thing where they were trying to get to a good signal to noise, and they're trying to have well-resolved galaxies. So in order to do that, some of the galaxies have resolutions of 4, 8. So the exact profile width varies between them. However, in terms of the number of resolution elements, there's typically 20 to 30 resolution elements per galaxy. So you're never in a poorly resolved spectral regime.
Okay, we have another question. Will there be a role for machine learning in this type of asymmetry classification with WALLABY?
There are people involved in WALLABY who are working on this, and I'm quite interested in using this in a machine learning methodology. The nice thing is the statistics are just simple numbers to calculate, and they can be used and then can be fed into your machine learning algorithms to see how they relate to the physical properties that you know about them, and then you turned loose on the larger sample.
Okay. I spend most of my time in the optical. If you look at the correlations that you see here in comparison with the optical light, or is there any association with the star formation histories, bursty, recent?
That's a really good question that unfortunately we haven't applied these to the optical yet. Again, in principle, there's no reason not to apply them to optical velocity profiles. And I think actually sort of doing a multi-wavelength approach of looking at asymmetries in optical and in H1 will actually be much more useful in understanding what's going on and talking about exactly what you're saying of star formation histories and starbursting.